Okay, here we are, last lecture of this course. We're going to talk just a little bit about life in the universe. A lot of this stuff has to do with what's now called the field of astrobiology. I wanted to give a big caveat here. And a lot of what goes into thinking about life on other planets has to do with kind of projecting about life on Earth and how that might be able to happen elsewhere. Specifically having to do with the field of biology, and then also chemistry, molecular chemistry, biochemistry, how molecules come together and then end up somehow eventually making it to what we call life. The caveat is that I'm not a biologist, I'm not a chemist, I'm a physicist. And I don't actually know all that much about biology and even about chemistry. As a physicist, I studied a lot about the sort of rules of the playing field, mechanics, and rules about forces and energies, and then also studied a lot about the really tiny things in our universe, subatomic particles, sometimes called elementary particles, and then also studied a bit about the very big scale, stars and galaxies, and gravity in particular, general relativity and how mass warps space-time. The in-between areas, I don't actually know that much about. I'm not going to try to explain too much about the processes that we define as life on Earth, having to do with chemistry and things like proteins and DNA, and it just wouldn't be very good. So I'm going to get very brief on those areas, but then also talk a little bit about things that we've done to contact possible civilizations beyond Earth and are still looking for possibly future contact with such civilizations. So this image is showing a couple of the places in our solar system where we think there either might be life today or there was life in the past. Mars is kind of front and center there, and then that is Europa, which is a moon of Jupiter. You think that there are liquid water, there are oceans underneath these like ice sheet that covers the whole moon. And then further out, like another star and a possible other planet around it that might also harbor life. So a couple of big ideas that you come up against when thinking about life outside of Earth, at least from a scientific perspective. One is what's now come to be called the Copernican principle, which basically says that there's nothing particularly special about where we are in the universe. Earth is a planet, like many other planets around a star, and sort of like rocky planet that's sort of relatively near its star. And our star is kind of midway-ish out from the center of the galaxy. Particularly special place. There are many stars like this. And our galaxy is a spiral galaxy, like many others that we see. So it seems to be that the conditions on Earth are not that unusual in the universe. And then since there's life here, the conclusion we would draw is that it seems pretty likely that there's life elsewhere in the universe. I think you could say this is like a generally accepted sort of view of the scientific community, is that, yeah, it seems pretty likely that there is some form of life elsewhere in the universe. The next sort of big idea you run up against then is, well, if there is life elsewhere in the universe, and if it's fairly common, then why haven't we seen it, or even been contacted by some other evolved civilization? This is what's known as the Fermi paradox. And there are many different reasons why it may be that we haven't been contacted or had any other clear indication that there was life elsewhere. These summarize most of the kind of possibilities of why we wouldn't have seen anything. Well, for one, could be that we would say intelligent life is rare. And intelligent, broadly, there means like life that is then capable of developing technology and utilizing that technology to either leave its home or send messages away, far away from its home. So it could just be that life isn't all that rare, but we might call intelligent life actually is rare. Another option is that intelligent life again, the kind that develops sort of technology, doesn't actually tend to last all that long, which may be that it tends to just sort of self-destruct. Could be that we have, or we are getting communications from other advanced civilizations. We're just not advanced enough to see them in one way or another, detect them. It could be that other civilizations have just chosen not to contact us for one reason or another, whatever reason. And then there's sort of a smattering of like, perhaps there actually is evidence that we've been contacted and it's just been lost to history, or maybe it's just not widely known of or widely shared. Get more conspiratorial, I guess, towards that very end there. But I don't know, maybe. If I were going to put money on it, I thought for a while that it's probably the case that there is other intelligent life that knows we're here and doesn't really care to talk to us, or is sort of waiting for us to stop being babies about existence and grow up a little. So if we're going to look for life elsewhere, then we need to know what to look for. So what are the things that make life possible? At least life as we know it, right? The kind of life that developed and evolved here on Earth. Well, for sure there are some key things. Water, particularly liquid water, liquid H2O, and some other sort of raw materials. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Some form of energy for life on Earth, like energy from the sun, or energy from digesting other organic life. And then finally, all these things need to be in an environment where some sort of complex chemistry can sort of take off, right? Or it can be allowed to happen. If the environment is just too volatile, then these elements, these raw materials, are not going to be able to build up and build bigger and bigger things. Just continually get broken apart. Or just never to get together in the first place. So this is my very brief diagram that I found from this nice place, Chemistry Land, showing the materials, these raw materials, basically elements, that make up the very fundamental things for how life works on Earth. So if you have hydrogen and carbon, then you can make things called hydrocarbons. Like methane is a hydrocarbon. If you add on oxygen to that, then we can construct things like carbohydrates and lipids, which lipids are very important for most cells. They're like the walls of cells that allow it to sort of keep things out. Add on nitrogen, and then we're able to build up amino acids and proteins. Along with sulfur, you can do more of that sort of thing. And finally, with some phosphorus, we can build up nucleic acids, RNA, and DNA. DNA is the carrier of our genetic information. These are some of the basic things we think life needs, the life as we know it, anyway. Which is not bad, because if you recall when I was telling you about the production of heavier elements in stars, all of these things are created throughout the process of a star's lifetime. As long as you have a heavy enough star, then the fusion processes restart after helium in order to produce carbon, oxygen, and then you continue a couple fusion processes along. We can make all these elements in heavy stars, and then when they go supernova, blow all that stuff sort of out into space, and this stuff becomes part of the interstellar medium, which can then be formed into new stars, but also the planets that end up forming around those stars. So these things are around. That's kind of the point that I'm trying to make there. Another interesting point here is that when trying to date, at least on Earth, when the first life evolved from very basic life forms, microbes or some such. I'm not a biologist. I don't know what the simplest life forms are, right? But taking people's word for it, that the simplest sort of life forms that we find in like fossils that date back a long, long time, billions of years. And from this kind of evidence, it seems that life was able to sort of take off or begin to evolve pretty quickly after the Earth sort of stabilized. So you recall in the early solar system, I told you that once the planets had formed, there was still very chaotic time for a while. You sometimes call it the time of like heavy bombardment, when the sort of pre-Earth had mostly formed, but it was still being smashed into by fairly large, like planetesimals and other debris that's still floating around in the solar system early on. But it seems like once that dies down, it doesn't take all that long for life to begin. I think the heavy bombardment period, I think, was like something hundreds of millions of years or something. And then first evidence of life that we find is some hundreds of millions of years after that. So I think it turns out that some of the oldest life forms that we've found are like fossils that date to like 3.5 billion years ago, which is about 1 billion years after we think the Earth formed. So pretty quickly, however you want to say it, it seems like once the conditions were stable enough that, life was going to start to form. And planets are around for quite a long time. Even when you think about a few hundred million years, planets are around for 10 times that, at least, not more. So all these we could say are like good signs for the possibility of life developing elsewhere. The basic building blocks are around, and once life has a chance, it seems to want to develop. Just some examples where those sort of building blocks might be found throughout the universe in things like comets. And at this point, I think the prevailing theory is that most of the water on our planet was brought to us by impacts of comets. So comets, if you remember, are mostly like icy bodies versus asteroids, which are mostly rock. So we think that early on in Earth's history, a decent amount of comet impacts delivered a whole bunch of the water that we have now. And possibly even some of the materials that were sort of the very basics before life was able to build up. Things like organic chemicals. And organic just means chemicals with carbon. Carbon turns out to be a very important chemical because of the way it bonds to itself and other things. So at least for the life as we know it, you might even call it carbon-based life. But it seems like comets, of course, have water, but they also have been found to have some of these other organic chemicals too. And this is just an image of it says gas and dust cloud, but like a molecular cloud, sometimes called the dark tower. Nice name. Yeah, if you remember when I told you about molecular clouds, that's when sort of the interstellar gas and dust clumps up enough together where the interiors end up being fairly stable regions because they're sort of surrounded by thick gas and dust. And so in those interiors, we've seen evidence of more complex molecules. And then also in those same regions is where stars are going to be formed, molecular clouds. Just more to say that the building blocks of life as we know it are out there. And plentiful might be a strong word, but like where stars form, where planets form, and what forms with stars and planets seems to all lend evidence to the case that life will tend to form in a lot of scenarios, as long as it has, in the end, that sort of stable environment too. Should say for sure, the only place in the universe that we know life has evolved is here, is on Earth. We've still not found any conclusive evidence of life outside of Earth. But the thing is, it's pretty hard to look for life, right? Even just looking within our solar system. So, we might get really lucky and at some point find fossil evidence of life that existed once on Mars, right? That would be really cool, be a strong confirmation. We could also get really lucky and one day send a probe to Europa that's able to get underneath the icy surface and take samples to find that there are actually microbes or things living in the ocean underneath this surface. Also really nice direct evidence of, yes, life does exist elsewhere. Still haven't found that. Still trying. These are sort of illustrating some of the places that we think we're most likely to find evidence of life, either in the past or presently. So as I mentioned on Mars, we've sent a number of rovers They go there for a variety of reasons, but one is to search for evidence of life that had existed on Mars at some point. We don't really think there's much life there now, or any. If there is, possible, be subsurface. It would be a while before we're able to get to figuring that out. It seems more likely that we would find fossilized evidence, because we're pretty sure, and as I told you a while ago, a long time ago now, we're pretty sure that Mars did once have liquid oceans, water oceans. And that was a long time ago, probably a few billion years ago, and that was before its atmosphere had sort of leaked away into space, and once the atmosphere leaked away, it couldn't stay warm anymore, and so any water that was there is probably frozen up, or maybe even evaporated. I'm not really sure. The drill holes there are from one of the rover's arms. The picture on the right is the rover arm, and little drill holes that it made, and drilling into rock that is found to be sedimentary rock, which only forms, we're pretty sure, only forms at least when water deposits layer upon layer of dust and like dirt onto a surface over and over again. So you build up these layers, which eventually form into a rock, sedimentary rock. So it seems pretty likely that there was once water, a lot of water on Mars, but a long time ago. Another one that I already mentioned is Europa. I told you about a while ago too, but pretty sure that there are oceans, or liquid oceans probably, underneath the outer layer of this moon. This is a moon of Jupiter. The sort of energy source that life might use in that situation might have to do with like the tidal heating of the planet's interior. Remember we were talking about the moons around Jupiter. I told you about this sort of like stretching and like kneading of the moons that happens because of the strong gravitational pull of Jupiter. Well, that generates heat in the interior of Europa, which is probably what also allows for liquid to even exist there, because it doesn't get enough sunlight for it to be warm enough for liquid water. So it seems like the tidal heating is giving energy to the interior to make the inside, or possibly a layer near the outside, be liquid water, which could also provide energy for life. Below that is an image from another moon, this one a moon of Saturn called Enceladus, which also seems to have liquid water underneath its outer layer of ice. When a probe flew by the moon, it actually snapped pictures of these like plumes, or these sort of like eruptions of ice and gas that was like spurting out of places on the moon's surface. So again, similar thing, you have liquid water there. It seems like it might not be a bad idea to try and check it out at some point. And there are, for sure, people attempting to send probes in one form or another to all these places. Already sent probes, but more, get an even closer look. One other place that we wanted to mention is also another moon of Saturn, that's Titan. And it's interesting because it is the only moon in the solar system that has a very thick atmosphere. And the atmosphere you can actually see in that image that was taken of Titan, where sunlight is going through the atmosphere and kind of making it glow, and you can see the orange color of its atmosphere. And we think even that little like really bright spot is actually a sort of a glint or like a reflection of the sun off of a liquid body on the surface of Titan. However, we're pretty sure that the liquid that is there is not liquid water, probably liquid methane. And there's an image up close of the surface, or part of the surface at least, and it has these features that very much seem to indicate that there is liquid there. And these are sort of features you get around bodies of water. So possibly not life necessarily as we know it, but could be some form of life there. So here, we've been able to send probes and look more closely at some of these things, even send landers to Mars. But once you get out of our solar system, it becomes exceedingly more difficult to look for life on other planets. Not that we're not trying, we don't have ways we're trying to do it, but it's really difficult. On the right here is an image that was taken by the Voyager 1 spacecraft. So as it passed Saturn, it sort of turned around and took a little snapshot towards Earth. So that white circle is indicating where Earth is in this image. So a little dot, right? This photograph is actually usually called the pale blue dot. So this gives you like some idea of looking at a planet from rather far away and thinking about like, how would you determine if there's actually life on that planet? No easy task. And this is even an image taken within our solar system. So if we're looking at planets outside of our solar system, ooh, it's tricky. Yeah. Some basic sort of benchmarks we might consider when looking for planets that might habit life or be able to support life. We sometimes say, like, is the planet habitable? Well, one thing that we generally say makes something habitable is if it's possible for there to be liquid water on that planet. And I told you about this concept a while ago. We were talking about exoplanets, but just to reiterate that we sometimes talk about this habitable zone for planets around stars, and that zone is sort of like the orbit, or that set of orbits, the whole range of orbits around the star, where we think liquid water could be present on the surface. So that means like the right temperature, or within the right temperature range, within the right pressure range. So where those habitable zones are can vary, based on the star itself, how much energy it's putting off, how large it is, and then also like on the planet, where the planet is, how large or small the planet is. And if we want to go beyond saying, well, maybe there's the possibility of water there, to saying, well, are there some of these other key building blocks that we think are needed for life, such as carbon and oxygen and nitrogen, sulfur and phosphorus. And the way we look for those, or compounds made out of those, is by trying to detect light from distant planets and looking at the spectra of that light, or looking for the spectral signatures of these elements, or maybe compounds that are formed out of these elements. So that's all just to say that, even if we find evidence of a planet that's in a habitable zone and spectral signatures of some of these building blocks, it's like, well, okay, that's great. That seems maybe like it's a habitable planet. But the question still is, if we're looking for life, we don't just want to know, is life possible on that planet? We'd like to know, is there life on that planet? So the other side of this is, how do we detect whether a planet is inhabited, meaning there is life there? Also a very tricky thing. Just mentioned that one way we think of going about that is by looking for signatures of not only the building blocks, those elements, but looking for specific elements or specific compounds, chemical compounds, that, as far as we know, are only really produced through the process of life. So the only reason that there's a lot of O2 in our atmosphere is because life at some point developed a process called photosynthesis, and one of the outputs of that process is O2. So if you look for a planet, and then you also are able to detect a significant amount of O2 in its atmosphere, that's a pretty good indication, we think, that there's life there. So again, really difficult, but we're still trying, and as technology gets better, our tries will hopefully be stronger, and maybe one day we'll be successful. I should say, at least, I think we've already found planets that we think are habitable. The question of whether there are planets that we know are inhabited, I don't think anybody's claiming that at this point still. So in the search for life outside of Earth, what I've shown you so far are like, well, literally go and look for life elsewhere, sending probes and possibly people to other planets and moons in our solar system to look for life. This one, look for life outside of our solar system, but generally you're depending on astronomy techniques, looking at spectra from distant objects in order to analyze and say what kinds of stuff is going on with that object. And then also even just looking at its orbit to say if it's in its habitable zone. Some other things that we've thought about doing and done in terms of looking for or trying to contact life outside of this planet are like sending things out into the universe and thinking maybe one day some distant civilization will find those things and be able to figure out what the heck they are. Another way might be to not send particular objects, but send electromagnetic radiation, like radio waves, out into space, trying to contact or send messages in one way or another to other civilizations. And then on the other side of that, just listening for the possibility that there are other civilizations that have been out there and are out there. They're trying to send messages to places like Earth. So from their perspective, alien life. So one of the things we've done thus far is send spacecraft through our solar system, and they do various scientific observations as they move through the solar system, but the end of that journey is nowhere in our solar system. So these crafts like Voyager 1 and Voyager 2, were sent off, I think in the 70s or 80s. Well, I'm not sure exactly. But their eventual destination is basically just out into the galaxy. And so what do you send along with a spacecraft that might encounter another civilization, extraterrestrial intelligence? Well, the spacecraft itself sends a message, right? So that there was some being somewhere who are capable of crafting this thing and booting it out of its own solar system. But beyond that, on the Voyager crafts at least, and I think other ones are like Pioneers and they had messages too, but on the Voyager crafts, each of them has a gold-plated record. I think it's actually a copper disc and then gold-plated on the outside. And it's not gold-plated just to be fancy. Gold is very non-reactive, and so the idea is that it's going to last for a long, long time. So on that record are encoded something like 100 photographs, 90 minutes of music from around the world, and greetings in almost 60 languages. And the scientists at the time came up with some way of telling this other civilization that finds this record how to make use of it. And so printed, or like inscribed on the back of the record, is instructions basically of how to use this information. It's something else. I don't know, I guess kind of just wild to think about like some civilization finding this in the very, very distant future and how long it would take them to figure out what the heck it says. Maybe it wouldn't be that long. I don't know. Hard to say. I don't want to go into too much detail of the instructions, but also on the record there is this sort of like starburst looking thing, point with a bunch of lines coming out. And that is actually meant as a pointer or a way to show that civilization where this disk came from. So those lines are to pulsars around us. So they indicate like the rate of the pulsar probably, and then the direction sort of to us. And where all those intersect is basically where Earth would be. So it's a very hopeful sort of thing, I guess. Don't hold your breath on hearing back from anybody though, because the spacecraft, even though they're sent out decades ago, are still barely sort of at the edge of our solar system. So both of them are now traveling at something like 60,000 kilometers per hour, or about 35,000 miles per hour. It's very fast, at least relative to our normal way of moving, very fast. But even at that rate, we expect that Voyager 1 is going to pass by a star in about 40,000 years. That star, Gliese 445. And around that same time, 40,000 years or so from now, Voyager 2 should also be passing by a star, Ross 248. We're both going to continue along, but the next passage that one of them might make by another star is Voyager 2, should probably pass by Sirius in about 300,000 years. Yeah. When we say pass near by a star, the first pass by is noted there are something like, we think like 1.5 light years away from that star. And by the time Voyager 2 passes by Sirius, I think it's going to be at least 4.5 light years from Sirius. So, who knows, right? If there is any life in those star systems, then how likely is it that it's even advanced enough to recognize that there is an object passing 1.5 light years away from the star? Who knows? I don't think the idea was really that those passes are actually going to result in another intelligent life form finding a spacecraft. I said that the gold plating was to make this record last. And I think when they estimated, how long this might last or be like reasonably usable is like 1 billion years. So the thought of when something might eventually find this record probably going to be quite a long time until that's even a decent possibility. If at all. Who knows? Who knows? Right, so the other thing that we do when looking or trying to find life in the universe is, like I said, we listen for messages that might come from other intelligent civilizations, technologically advanced civilizations. So other civilizations that are capable of producing and directing radio waves. Also, more recently, we've realized that if you really, really condense or confine a light pulse, like visible light pulse, then you might be able to send information very far, or a message very far that way too. So there's another side of SETI now that we might call optical SETI, which is looking for signals sent in much higher energy parts of the electromagnetic spectrum. So SETI is an acronym for the Search for Extraterrestrial Intelligence. The image on the left there is of a radio telescope array. And so for a long time, it seemed to make the most sense that if we were going to send a message out, it would be with radio, or the radio part of the spectrum. So the other end of that is thinking that, well, other civilizations might be trying to send radio signals. So we use these radio telescope arrays to try to listen for them. There are a lot of complications with that, though. And this leads to what's generally called the cosmic haystack problem. It's like you're looking for a needle in a haystack. And so these are a whole list of questions that the book threw out in terms of this problem. But I think for the most part, you can kind of sum it up as like, where do you actually look for a signal from? And how the heck do you recognize a signal from another form of life? And a lot of these questions get maybe more into the kind of details of like looking for signals in radio part of the spectrum and having to do with frequency and like the strength of the signal. But, for the most part, for us, it's like, where do we even look for these signals to come from? And how do we know what to look for? Or how do we recognize something if it even does come? If anything, the whole process of science and the evolution of our understanding of the universe that's come to now has shown us it's that we tend to severely lack in imagination sometimes. So yeah, this is one of the examples of like the resolution of Fermi's paradox, where maybe there's already signals coming to us and we just don't recognize them. We're not able to filter them out of the rest of the sort of natural signals in the universe. And so one final thing I'll say about what we might look for are, say, like very advanced extraterrestrial civilizations and technologies. So, you could imagine, and people do in like science fiction and such, where we're able to survive and not destroy ourselves for long enough that our technology advances very, very far to the point where you could even consider that we might do something like harvest energy from a star directly. It's possible at least to conceive of some very advanced civilization constructing these sort of like mega structures. And one of those ideas is what's known as the Dyson sphere. So this is basically like some form of structure around a star that sort of takes in the energy of that star, or harvests sort of the energy of that star in order to utilize it to do something else. If this sort of thing is out there, then that's something else that we might look for. It's kind of the idea. Because if you see a star that is, maybe dimming and getting blocked in very weird ways, hard to explain by anything like other stars or planets. Eventually it might conclude that maybe we'll eventually see a star that has this sort of mega structure around it. And in fact, one of the missions of this Wide Field Infrared Survey Explorer, or WISE, is to look for evidence of structures just like this. Still haven't found it. Not yet. So the last point to make about looking for life outside of our planet is to think about what even is the possibility that there is life outside our planet. I kind of just told you earlier on that, it seems pretty likely that life is going to evolve. If it has a chance, it's going to do it. And it seems like in the normal process of stars and planetary formation, there are chances for life to evolve. But if we're curious beyond that, not just life, but then intelligent and maybe technological civilizations, what are the possibilities that there are those out there, right now, or in some way that we might contact? So this gets at what's known as the Drake equation, which is basically a bunch of factors for different aspects that need to build up in order to make for a civilization that we might encounter at some point. So the original Drake equation is along the top there, and some of those factors are like the rates of star formation in the galaxy, the fraction or the percentage of stars that form with planets, and then the number of planets or the fraction of those planets that seem to be habitable for life, and then a few other sort of percentages or fractions for whether or not life actually evolves, or what's the likelihood that life actually evolves, what's the likelihood that intelligent life evolves, what's the likelihood that life evolves, or that intelligent life develops technology in order to receive signals. And then the final variable up there is what is the length of time that a technological civilization is around for. So that's the original Drake equation. The bottom is sort of a simplified version of it, which sort of puts a number of those factors together into saying one factor, which is what is the likelihood that a habitable planet forms, and then the other factor being what is the probability that technologically advanced life will evolve out of that habitable planet, or on that habitable planet. And still with this last factor of how long does that technological civilization tend to last. There's just ways of thinking about the chances that there are other civilizations that we may end up getting in contact with at some point. So I would say that probably the largest, or one of the largest uncertainties in this whole idea, this equation, is L. What is the length of time that a technologically advanced civilization will last? It's really hard to know, because we only have us so far, right? And you can think of technologically advanced in a number of different ways, but as far as communicating with other star systems, right, we probably at least need to be able to send radio transmissions. So you think about when were radio transmissions first developed, it was something like 130 years ago. Really not all that long ago. And then how much longer will we be around? That's anybody's guess. In general though, if this length of the civilization is not very long, a few hundred years, it's not a good chance that we're going to encounter many other civilizations. If that length of time is thousands of years, or tens of thousands, million years, likelihood gets much better that we'll probably encounter some other intelligent life forms. But again, jury's still out on that one. And now we've come to the end. I've told you a whole lot about astronomy this semester. I really hope that you've learned some things. Most of what I said made sense. Who knows, maybe sparked your curiosity, and maybe you're doing more reading about astronomy now, or just interest in the origins of the universe. Or maybe like me, you just found out that you also really like pictures of space. So I thought I'd end this with this excerpt from part of the message that's on Voyager, from those gold records. This was in the textbook. I read it. I rather liked it. So I'm just going to read it for you. We cast this message into the cosmos. It is likely to survive 1 billion years into our future, when our civilization is profoundly altered. If another civilization intercepts Voyager and can understand these recorded contents, here's our message. This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We hope, someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination and our goodwill in a vast and awesome universe. So I think I'll just leave it there. It's been fun. Maybe I'll see you around. But either way, I wish you the best. Adios.